I'm not sure if this class is called general relativity or relativity, but anyway, most of it's going to be general relativity. That's me, and I'm at Imperial College. Part 1, we'll be looking at the status of, well, relativity. Back when Einstein decided to make it general. So that will be that will include gravity prior to 1916, and then the motivations for general relativity, which we'll abbreviate as GR. Part 2 will be geometry, because as you probably know, Einstein's theory of gravity is a theory of curved space-time, and he makes use of the work of Riemannian geometry that was well known in 19th century mathematicians. So that will be tensors, curvature, and geodesics. So that's setting everything up for this part will be just mathematics. It will be setting things up for the physics, which is embodied in Einstein's equations. And first of all, we'll look at the derivation of Einstein's equations, what led him to write them down in the first place. Then we look at solutions of Einstein's equations. And this will include things like the Schwarzschild solution, black holes, and so on, and also exact cosmological solutions. And it's with these solutions that we perform experimental tests of Einstein's theory. And I'm sure you're not surprised to learn that it has passed all the tests that have been applied so far. And then finally, which I guess it's its own section, but we could also lump it under Einstein's equations, we'll have a brief introduction to cosmology, because the origin of the universe, the Big Bang, the expansion of the universe, the acceleration of the universe, all of these rely on Einstein's general theory of relativity. Now, the books, this is going to be an old-fashioned lecture course. Everything will be on the blackboard. Everything you need to know will be up here, no handouts or anything like that. So what books are we going to be using? The main one is Gravitation and Cosmology by Weinberg. And that's published by Wiley 1972. Another book that I learned relativity from, which I think is a nice one, is Principles. It's a bit old-fashioned, I suppose, now. Principles of Relativity Physics by Anderson. And that's published by Academic Press. (1967). And then there's the classic, which I always think explains relativity better than anybody else. And that's the man himself. And that's the version I have is Chapman and Hall, 1980. Now, round about this time, we're going back in history to 1916 or thereabouts. Einstein wrote a postcard to his friend Arnold Sommerfeld, and he said, "Of the general theory of relativity, you will be convinced once you've studied it." I hope that applies to you too. "Therefore, I am not going to defend it with a single word." Well, that doesn't apply. I've got to defend it, and I hope you're convinced at the end of the course. So, what questions was Einstein asking himself at this time? Haven't got the hang of these boards yet. Thought we lost it for a moment, but you can still see it there. Okay. This first lecture is going to be more words than equations, but don't worry, that will change. In special relativity, velocity is relative. But not acceleration. In special relativity, we'd learned, and we'll say a bit more about special relativity in a few minutes, that the laws of physics are the same to two observers if they're in uniform relative motion. But they're not the same, according to relativity, if they're accelerating with respect to one another. Why should that be? Einstein asked. Another way of posing the same question is, what is so special about inertial frames? About which we'll say more in a few moments. The second puzzle was gravity. The theory of gravity that had stood the test of time up until that point was Newton's theory of gravitation. But Newton's theory was incompatible with special relativity. Curiously, at the time, Maxwell's equations of electromagnetism, on the other hand, which had been around, I don't know, a bit longer, 50 or so years. Maxwell's equations of electromagnetism were compatible. It's a rather strange historical fact that the theory that Maxwell dreamed up in the mid-1800s turned out to be relativistically invariant, even though he didn't design it to be. But we'll see, Maxwell's equations of motion are compatible, but Newton's theory of gravity is not. So that's the puzzle. A third question has to do with the equivalence principle, which was basically the observation that all things fall at the same speed in a gravitational field. There's this famous but possibly apocryphal story of Galileo dropping weights from the top of the Leaning Tower of Pisa. And according to Aristotle, the heavier weights should hit the ground first, but Galileo found that was not the case. They hit the ground at the same time. Things fall at the same rate, irrespective of how heavy they are. Now, Einstein was intrigued by this. This is probably what got him thinking most of all. So he asked himself, what's the theoretical explanation for the empirically well-known fact that all bodies fall with the same acceleration. In a gravitational field. It's not true in an electromagnetic field, by the way. The analogous statement, the bigger the charge, something has a charge, the bigger the acceleration it feels. In gravity, that's not the case. Another way of saying this is the equivalence of the gravitational and inertial mass. In Newton's law, we have force equals mass times acceleration. And in gravity, we have that the force between a body of mass big M and another body of mass little m is gmm over r squared, the inverse square law. And the fact that everything falls with the same acceleration is compatible with the fact that the m that appears on this side of the equation is the same m that appears on that side of the equation. But that's an assumption. Why should the m that appears in the force law be the same m that appears in Newton's law of acceleration? That's the puzzle. It's empirically true, but why should it be true? And connected to all of this was the meaning of coordinates in physics. For example, a straight line in one coordinate system need not be straight in another. Now, with Newton's laws, one has the feeling that unless you're acted on by an external force, particles continue with uniform motion. So they follow a straight line, in other words. But what is a straight line? A straight line is a coordinate-dependent notion. What's straight in one coordinate needn't be straight in another, in general. So all these were going through Einstein's mind at the time. Special relativity, which had worked very well in the domain for which it was supposed to work, which was in the absence of gravitational fields. But when you put gravity in there, things start to get a little puzzling, because you'd like to be able to know why it is that acceleration is not as relative as velocity. It seemed to Einstein they should be. Secondly, the theory of gravity that people have been relying on, and which they still rely on today for most practical purposes, was Newton's theory of gravity, and yet it was incompatible with we had two great theories, Newton's theory of gravity, Einstein's theory of special relativity. They didn't fit together. And if you look at the history of science, you usually find that when big ideas come into conflict, that this augurs some new revolution. Something has to give. Something big has to give. Either special relativity has to give, or Newton's theory has to give. And we face a similar situation today with trying to unify general relativity and quantum mechanics. They don't seem to fit together in the obvious way, and something big has to give there too, though we're not yet in a position to conclude what the new theory is. That's one of the most exciting topics of research at the moment. So this dilemma posed itself back in 100 years ago, and the other puzzles were this fact that everything falls equally in a gravitational field, and what are coordinates all about. So let's just remind ourselves a few things about special relativity. I'll be consistent and write in capitals if I can find the eraser. Before I do this, are there any questions? Don't feel inhibited. Even if it sounds a stupid question, ask it anyway. Yeah.
When you say, why should acceleration be absolute? By absolute, do you mean everyone agrees, regardless of the frame they're in, about who's accelerating and who's not?
Good question. What I mean is that the laws of physics should be the same, whatever coordinate system you're in, even if one is accelerating with respect to the other. So that's more or less what you said. In special relativity, if you and I are moving in uniform relative motion, we'll agree on what the laws of physics are. But we won't agree if one of us decides to accelerate. Then you have to change the equations. Now, Einstein said the right theory should be one where you don't have to change the equations. The equation you write down is equally good, even if you're in a frame that's accelerating. Now, what does that mean? How you actually achieve that is not obvious, but that's what the goal we're aiming at. Any other questions? You see, I think I know what you're driving at, that somehow you know when you're being accelerated, right? You feel a jolt, or you can... It's different from just uniform motion. So that observer dependence and the independence of the laws of physics have to be worked in together in some clever way to keep everybody happy. And we'll see that Einstein's relativity does that. But let's just remind ourselves a bit about special relativity. And I won't do everything on special relativity today. I'll mention a couple of things. And in the course of the lectures, we may return to look at special relativity in more detail. And relativity is all about invariance. In fact, most of physics is about invariance, about symmetry, about what things stay the same when you change other things. And what special relativity is about is that our equations will stay the same even when we make Lorentz transformations of the coordinates. And we'll see what Lorentz transformations are. They're called Lorentz transformations because Lorentz himself had some ideas about relativity which he didn't quite articulate as clearly as Einstein, but he got the right transformation laws. So let's look at some observer O prime moving, let's say, for simplicity, along the x-axis. With velocity v relative to some other observer, which we'll call O. Then the Lorentz transformations say that the time as measured by observer O prime is related to the time measured by observer O, but with a term that mixes in the space coordinate of observer O. So here's the setup. O prime's moving relative to O with speed v. And if he's moving along the x-axis, the y and the z coordinates are just the same. That won't be true in general, but in this simple example it is. Now you can verify that this infinitesimal distance in a four-dimensional space-time remains invariant under these transformations. Now I've chosen to work with infinitesimals because that's the way it's going to be in general relativity. Of course, it would be equally true if I'd written c squared t squared plus x squared plus y squared plus z squared. But it's more appropriate for future use to focus on infinitesimal distances. And as Einstein's colleague Minkowski noted, we can rephrase this in the language of a four-dimensional space-time. We introduce coordinates x mu, x0, x1, x2, x3, where x0 is c, speed of light, times t, x1 is x, x2 is y, x3 is z. And this notation, of course, proves to be very useful because long, complicated expressions can be written in a nice, neat way. So those Lorentz transformations tell me that I have a four-vector in the primed frame, and it's related to a four-vector in the unprimed frame by these transformations, which will be represented by a 4x4 matrix, which, if I've got my gammas and betas correct, looks like that. And I can abbreviate that by saying x prime mu equals the sum from nu equals 0 to 3 of lambda mu nu x nu, where lambda mu nu is the 4x4 matrix. So this equation is neater than this one, but we can go one step further using the convention that Einstein himself introduced. And that's to say, if an index is repeated, and in this case it's the index nu, we're summing over nu from 0 through 3, then we drop the summation sign. That's just understood. So whenever you have a repeated index, and as we'll see when we come to do tensors more thoroughly, that if it's repeated, one will always be up and the other will always be down, that whenever we have that situation, it means we're summing over the repeated index. And using the same rule, this infinitesimal distance in this four-dimensional space-time can be written as eta mu nu dx nu dx nu, where eta mu nu is a 4x4 matrix with diagonal entries -1, 1, 1, 1, and zeros everywhere else. And this has a name. It's called the Minkowski metric. So what this means in full, if we were to write it out, would be the sum from mu equals 0 to 3, sum nu equals 0 to 3, eta mu nu dx mu dx nu. But because the index mu is repeated and the index nu is repeated, we don't need to write down the summation signs. So we can write those Lorentz transformations in the Nita form as well. It says that the nu coordinate in the prime frame is lambda mu nu x nu. Well, we can go one step further. Lorentz transformations leave invariant that line element, but there's a more general set of transformations which leave it invariant. I can also add a constant term, a mu. And this, if I combine the Lorentz transformations and the constant term, these are known as Poincare transformations. Now you can check that if I put any old matrix there, lambda mu nu, the line element won't be invariant, but it will be invariant provided and I'm summing over indices, lambda mu alpha, lambda nu beta, eta mu nu is eta alpha beta. So that is in fact the definition of a Lorentz transformation. It's given by any matrix that obeys that equation. Now, you'll notice that this is not a four-dimensional space in the usual sense. It's not a four-dimensional Euclidean space, which would have all ones down the diagonal. It's got a -1 in the top corner, so time is distinguished in that sense, that it's the four-dimensional space-time has signature 1, 3, as we call it, not signature 0, 4. It's an interesting question why nature has that signature. Why are there not more times? Well, if you try and write physical theories with more times, you get into difficulties, but so most people ignore the question, but it's an interesting question. And I think one day when we have a theory of everything, it should in particular tell us why space-time has, not only what the dimension of space-time is, but its signature, 1, 3. But again, we don't have such a theory at the moment. Now, precisely because there is a minus sign, you have to be careful because the Minkowski metric is used to raise and lower indices. So a vector with a downstairs index, which is called a covariant vector, if I've got it the right way around, and a contravariant vector has an upstairs index, and they're related by v mu is e to mu nu v nu. So that means v naught is e to naught naught v naught is minus v naught, whereas v1 is e to 1 1 v1 is plus v1. So you have to be careful in raising and lowering indices to do it consistently because the signs are different. Is the summation convention something that you're familiar with? Okay. So I don't need to dwell more on that. Any questions? Yeah? Do they use the same signature?
Yeah, the -1.
Good question. Good question. Probably not. Life is awkward usually, and everybody has their own conventions. And I've got the feeling that Weinberg
right?
uses the opposite one.
We are using Weinberg.
I'm sorry?
The textbook is Weinberg we are using.
That's what I wrote down.
Yeah, so that uses -111. Mostly positive.
It uses the one I'm using, is it?
Yeah.
Good. Well, that's one good thing. Well, I'll take your word for it. I can't find it now. But different textbooks use different conventions, and you just have to learn to deal with it. The same is true with Riemann tensors. People have different sign conventions and so on. So you just have to remember that everyone's got their own conventions. Yeah.
Probably not a very important question, just about names and notation. Over there, you have the gamma matrix separate from the translation matrix, so it looks to me like gamma represents the just Lorentz transformation. And below that line, you have gamma Zeni matrix that
Lambda.
Yes, thank you.
Yeah.
That didn't alter the Minkowski metric, but don't translations also satisfy that equation? Or I guess perhaps you can't even come into that form.
Well, these are, group theoretically, these are separate. There's the translation group, and there's the Lorentz group. And if you put them together, you get what's technically known as the semi-direct product. But you don't, the only information you need about lambda is this. And the only information you need about A is that it's constant. And that's all you need to know. That's the definition. So lambda doesn't care what A is, and A doesn't care what lambda is. But you can make a bigger group by putting them together, and that's called the Poincare group. It's often, if you read textbooks on special relativity, they often go into all kinds of what I find complicated axioms about speed of light being the same, and I don't know what. Everything you need to know about special relativity is in that one equation. The laws of physics are invariant under this. That tells you everything you need to know about special relativity. All these lists of postulates and so on, unnecessary. And you needn't even mention the speed of light. Though you can if you like, but it's not necessary. Well, just to get a feel for special relativity and why it's compatible with Maxwell's equations, and why, and summation conventions and all that, I'm just going to finish off by writing Maxwell's equations in 4-vector notation. So in 3-vector notation, we have these equations. You notice there's an asymmetry that the electric equations have a source and the magnetic equations don't. That's just reflecting an empirical observation that we see electric monopoles in nature, but we don't see magnetic monopoles. However, theoretically, you could include magnetic monopoles. And most of our the theories we like most in attempting to unify gravity and quantum mechanics have magnetic monopoles, even though we haven't seen them yet. But so bear that in mind. But the conventional wisdom is there's a source on the right-hand side for the electric field but not the magnetic field. Now we can combine these equations into the following: d mu f nu rho plus d rho f mu nu plus d mu f rho mu equals 0. And notice there's a cyclic permutation of the indices. And we can write these equations as d mu f mu nu equals minus j mu. Where E1, E2, E3 is F01, F02, F03, and V1, V2, V3 is F23, F31, F12. J naught equals rho. And J1 equals I had the source with an upstairs index here and downstairs index here, but they're the same thing. So you can verify that Maxwell's equations, which look a bit complicated here, look simpler here. And you can even write this in a more suggestive form as d mu star f equals 0, where star f is, I think there's a factor of a half. And we'll be doing more about this in tensors, but I've introduced a 4-index tensor epsilon, which is equal to +1 if the indices are an even permutation of 0, 1, 2, 3, -1 if it's odd, and 0 otherwise. So you might think that there was a certain symmetry between f and f star, but it's spoilt by the source term. But if you had a magnetic source, you could restore the symmetry. And electromagnetic duality is something that takes f into f star and electric charge into magnetic charge. But we're not going to deal with that today. For today's purposes, I just want to show you how two things. First of all, complicated equations can be made to look rather condensed. In fact, mathematicians would go further and write this as df equals j, d star f equals 0. So you can get even more condensed if you want. But the important observation is that although Maxwell perhaps wasn't fully aware of it, his equations are compatible with Lorentz transformations, because if you can check that if you transform everything in the way that Lorentz said you should, these equations stay the same. So you get the same equations for two observers in uniform relative motion. Yeah?
Actually, the differential form of the Maxwell equation with star should be in the d equals j star. No, I mean the star should be in the first equation because it's
yes, thank you. Yes, yes.
They already
d star f equals j, df equals 0. Thank you. Any other observations or questions? Well, next time we'll have a look at the equivalence principle, and in particular we'll talk about Einstein's famous elevator experiment. Einstein liked to think about thought experiments, Gedanken experiments, and one of his famous ones was to imagine somebody who's in an elevator with no windows, so he can't see what's going on outside, and compare what he would observe if he were in a gravitational field and what he or she would observe if they were in the absence of a gravitational field but suffering an acceleration. And it was thinking about things like that that got him to think more closely about the equivalence principle. And that was where his genius lay, in homing in on what was important. And the elevator experiment is a crucial ingredient in his theory. So we'll see you again tomorrow. Thank you very much.